Hello everyone, my name is Jing Wang and I'm a PhD candidate at University of Colorado Boulder. Today we're going to cover data-driven prediction of occupant presence and lighting power, a case study for small commercial buildings. This research is part of the DOE-funded project Comprehensive Client Permissive Priority Optimization, and this is a collaborated project with PNNL and Oak Ridge National Lab. And the goal of this project is to develop a real-time load prioritizing and flexibility quantification framework for demand response deployment. And as we can see here in this diagram, a key part of this framework is to predict real-time pliability of building loads. And there are some challenges in terms of that. The first challenge comes from the uncertainty in building load prediction, and this is mostly attributable to the stochasticity of occupant behavior. This Markov chain here kind of describes how stochastic human behavior can be inside the buildings. And another challenge is that our traditional building energy simulation tools usually only use prescribed static hourly schedules for both occupant presence and building equipment. And the last challenge is that in reality, the occupant sensor data is often unavailable. So the research question we're going to answer today is, how do we predict building occupancy and power demand on a sub-hourly basis without occupant sensor data? First, let's take a look at the definition of occupant behavior modeling. Let's say we have a building here. It's either a residential building or a commercial building. The first step for occupant behavior modeling is called presence modeling. It's to predict whether or not the human are inside the buildings. And this is usually done with probability models. And then use the presence information as input. We can start to predict the occupant behavior. And here the behavior means the interactions between the occupants with the building systems, such as the lighting system, water heaters, or thermostats. And this part, there is a common method is to use Markov chains to predict occupant behavior. And here the physical model, the building systems can be as simple as a rated power value or as complicated as a whole physics-based model. And occupant behavior modeling usually can be used to inform building power demand prediction and further power flexibility determination, and or to predict building occupant thermal comfort. So to summarize, the first step is to predict occupant presence in buildings, and then predict occupant behavior, and use that results to determine the schedule of different equipment, and further use that for equipment control or power demand prediction. Traditionally, only these two steps are included in building energy simulation tools, and they usually don't have these two modules inside them. And here is the methodology we adopted for this paper. First, we did a literature review, and we found that there is a strong correlation between occupant presence and light switching behavior. For example, the switching mainly takes place when entering or vacating a space. And further, the switch-on probability of lights on occupant arrival exhibits a strong correlation with the minimum daylighting illuminance in the working area. And for switch-off probability, it has a strong correlation with the expected length of absence. For example, if the occupant only expects to leave the building for 1 minute, most likely he won't turn off the lights in his office. And based on that, here's the flow chart we used for extracting presence information from lighting power data. So first of all, we interpreted the lighting power data for occupant presence information based on these assumptions, and then use that interpreted presence to train the logistic regression models for occupant arrival and departure. And then that regression model is implemented in Modelica for presence predicting. And then we predict lighting power based on this presence information. So if the lighting system is simply on-off control, then we simply times the presence with the nominal power of the lighting system. However, if the lighting system is multi-stage control, then we need to train some extra lighting power status model and also implement them in Modelica. For example, here are the 2 case study buildings we used in our paper. One is ice cream shop and the other is bakery. We see a difference of lighting power shape in these 2 buildings. For this building, the lighting power shape is very regular for each of the day. But for this building, we see 2 different values for different days. So we further divided this lighting power into 2 parts. This part is the base lighting power, which has a similar shape as this one. And this one is the actual lighting power shape. It only happens for a few days of the week. Here's the logistic regression model equation we used. And this is the shape of a logistic regression model. It has an S shape. So here P represents the probability of occupant present in the building, or for extra lightings, it means extra lights is on in the building. And the independent variable X here, for predicting occupant presence, we use time of day as the independent variable. And why do we choose logistic regression? First of all, it is a linear classifier, so it's easy to train. And it can reach the same level of accuracy as other nonlinear classifiers. And also for implementation, it is easy to be implemented in Modelica. We used the data of summer 2018 for the training. We used the June, July data for training and August data for testing. And the accuracy of the classifier is quantified with this equation. We used the number of correctly classified points divided by the number of total data points. And for example, in this table, the red numbers means the data point is correctly classified, and use that number to divide the total number of data points inside this table. And next step, for lighting power description, we used a method called multi-stage lighting power description, which means we divided the lighting power into n stages, and it consists of base part and some extra lighting parts, and P is the total lighting power. This AI here is a binary variable generated with a random number generator. It indicates the status of the base power or extra lighting power. And for extra lighting model in the bakery that we see earlier, we found that the status of the extra lighting actually has a correlation with day of week. So we chose the independent variable for this part to be day of week. However, we also found that the total frequency of extra lights to be on in 2018 is only about 9%. So to deal with the imbalance of the data set, we used the SMOD method to deal with the imbalanced data set. Here are some results. In these figures, we see that the regression models actually align with the data points very well. And this table lists the accuracy for all of the regression models. The accuracy is all above 84%. And here's the implementation of the Modelica model. As input, this is a presence prediction model, and it is a stochastic simulation model. For every 2 minutes, a binary variable generator will randomly generate a binary number, and the probability of this number being 1 equals the probability at that time of day, calculated by the logistic regression model. Here's the monthly simulation for lighting power inside the bakery, and we used the following matrix to evaluate the results. Generally, we noticed oscillations in the predict lighting power. This is because we set the prediction interval to be 2 minutes. However, this interval can be adjusted based on the user's needs. And second, for extra lighting prediction, we noticed in reality there are only 4 times of extra lights on, but in the model we predicted 9 times of extra lighting on. And here's the some more results for the probability of bakery models. We see they basically align with each other very well. And here's the RMSE for each of the models. For presence prediction, the RMSE is about 0.1, but for extra lights, it's 0.15. Because we see that the prediction for extra lights is pretty off. This is because of the imbalanced training data sets. And for probability of extra lights on, we see that the numbers for other days are aligned with each other, but the probability for Tuesday and Wednesday are pretty off. And here are some more values. For peak lighting power prediction, we see that for single stage prediction, the peak power prediction is very accurate, but for multi-stage, double stage prediction for the bakery, the accuracy is worse, but generally speaking, the peak power prediction accuracy is below 6.9. And we also looked at the NMBE for the lighting power prediction. We looked at monthly, weekly, and daily NMBE, and we found that there's a better performance of the prediction models in longer prediction horizons. Here, we see that for daily prediction, we have a worse accuracy. This is because the NMBE quantifies the accumulated performance of the prediction model. So we would say this kind of model is more applicable for longer-term energy consumption prediction. For energy consumption prediction, it will have higher accuracy than daily predictions. So to conclude, in this work, a method for occupant presence learning and reproducing based on lighting power data is proposed and validated. The proposed models can predict daily lighting peak power within 2.4% relative error, And stochastic models can be very accurate for longer-term predictions. However, they cannot predict uncommon events, and this leads to larger short-term prediction errors. And the limitation of this work is not having the ground truth data for occupant presence, and in the future, we also want to cross-validate the occupant presence with other appliance usage data. Thank you.